Chapter 8 is on exponential and logarithmic functions. It is actually my favorite function or favorite chapter and my favorite type of stuff to deal with in math. Y equals 2 to the x is an example of an exponential function. Exponential means the variable is an exponent. So here we have 2 to the x as opposed to 2 times x, which is linear, or x squared, which is quadratic. 2 to the x is exponential, where the variable is an exponent. These aren't polynomials. They don't follow the polynomial rules. In fact, their graphs look pretty interesting compared to the rest that we've seen, and we'll talk about those. So I'm going to take y equals 2 to the x. I'm going to graph it over here, and I'll plug in points over here, and all this stuff can be done on your calculator. I'll start with the easy one. If I plug in a 0 for x, 2 to the 0 is 1. Anything to the 0 power is 1, so 2 to the 0 is 1, and that's the point 0, 1. 2 to the first is 2, 2 to the second is 4, 2 to the third is not 6, 2 to the third is 8. It's 2 times 2 times 2, which is 8. 2 to the negative 1, if I plug in negative 1 for x, take a second and see if you remember what 2 to the negative 1 is. That would be 1 over 2, or a half. 2 to the negative 2 is 1 over 2 squared, or a quarter. And 2 to the negative 3 is 1 over 8, or 0.125, an eighth. It has these dots that follow this curve here, and this is called an exponential growth function, exponential growth curve. But I can graph the whole line here. You'll note it gets really big really fast, because each and every time this number x increases, the y value doubles. X to the fourth would be 16, or 2 to the fourth is 16, 2 to the fifth is 32. Each time the y value doubles, so it increases very quickly. That's why it's called exponential growth. And as you go further and further to the left, these values here get closer and closer to 0, but they never actually touch 0. In fact, there's a line that every exponential graph has that we call an asymptote, which is a line that the graph gets closer and closer to but never actually touches. So in this case, it won't always be this way, but in this case, the asymptote is the line y equals 0. The y value will keep getting closer and closer to 0 as this number gets more and more negative, larger in the negative direction, but never actually touches 0, and that's called an asymptote, which is spelled like that and is a funny sounding word. Y equals 2 to the x is really the parent function. All exponential growth functions can kind of be looked at as some transformation of y equals 2 to the x. Here I'll take the same graph. Here's y equals 2 to the x right here. I'm going to do a 3 in front of it, so 3 times 2 to the x. If I plug in a 0, 2 to the 0 is 1, times 3 is 3, so that's the point 0.03. If I plug in a 1, 2 to the first is 2, times 3 is 6. If I plug in a 2, 2 squared is 4, times 3 is 12. And plug in a 3, 2 to the third is 3, times 8 is 24. And what I'm hoping you're noticing is that all of these values here are just 3 times as high as these ones here. This was a 2, this is a 6, this was a 4, this was a 12, this is a 1, this was a 3. And I can go backwards. 2 to the negative 1 is a half, times 3 is 3 halves, or 1.5. 2 to the negative 2 is a quarter, times 3 is 0.75, 3 quarters. And then an eighth times 3 is 0.375. These still share the same asymptote. This graph will still get closer and closer to 0 as we go to the left, but as you go to the right, it increases very quickly, in fact 3 times faster than its parent function. Whoa, I'm going to draw a very poor exponential graph here with my mouse. Yeah, not bad. Exponential growth, an asymptote at y equals 0. We've covered lots of types of equations so far, and they all had some critical point. Some point where we would start from, or a point we would look for, or a point in the middle. With absolute value equations, it was this corner point. With quadratics, it was this vertex. For square root functions, we call it the starting point. It's also kind of like a vertex, but there's always this point here that things would start at. For exponentials, I made up a term called the 0, 1 point, which basically means this value right here. If you look at the parent function, this 0, 1 point, you plug in a 0 for x and get a 1 for y, is kind of the critical point. It doesn't always come out to 0, 1. Here it came out to 0, 3, but the point is 2 to the 0 was 1, so I plugged a 0 in for x and got out 1, then times 3 made it that 3 there. In fact, exponential functions can follow that AHK formula that we've seen in all of our classes. Or all of our functions, excuse me. I'll go through this quickly, but HK I call the 0, 1 point, and it's pretty rarely actually the point 0, 1. It very rarely actually comes out to the coordinate 0, 1, but the point is if I plug something in to make this whole thing equal 0, b to the 0 is 1, and it's a times 1 plus k. The parent function moves right h and up k, just like everything else. The line y equals k is the asymptote. If b is the base, this is the important thing. If the b value is greater than 1, the graph has growth, and if the b value is between 0 and 1, the graph has decay. The b value is never actually negative. The a value can be negative, but not the b value. The b value is always positive, and it's also never 1. It's always less than 1 or greater than 1. You can ask yourself what would happen if the b value equaled 1. It's a pretty quick thing to figure out. We call a, this a value in front, the coefficient of growth or decay, depending if the graph is growth or decay. It's really the dilation factor, and your book has very good examples of this in graphs in section 8.1. I think your book does a good job of handling this. So let's graph this one. In fact, I've already plugged in the points and found what they'll come out to. 2 times 1/3 to the x minus 4 is our graph. Because this b value, because our base is less than 1, it's a third, the graph has decay. As the x values are negative, it gets very, very big. As the x values are positive, as the x values are positive, it starts shrinking and shrinking and shrinking until it gets closer and closer and closer to a line that it'll never touch. And that line in this case is the line y equals -4. I could keep on plugging in numbers like 4 and 5 and 6 and 7, and as I plug those in, these will all come out to numbers that get closer and closer to 4. In fact, I'll show you on my calculator. Eventually, the calculator says that it actually touches 4. The calculator will show that because it has to round eventually, but these graphs never actually will touch 4. It just kind of looks like they do. So I'll pull up my calculator and show that to you. I'm going to type in y equals 2, then parentheses, 1 divided by 3 to the x, because there's my to the x, minus 4. If I look at the graph, just push the graph button, there's my exponential curve, very, very, very quick decay until it flattens out in a hurry. Look at my table, here's my x values at 0, I get the point 0, -2, had the point -1, 2, and there's me going with x getting negative, it gets bigger and bigger. And when x gets positive, it gets smaller and smaller and smaller. Pretty soon, it can't keep showing all the 3.99, so it starts saying it had the 0.8 -4, but it's really just -3.99999, and the calculator has to round eventually. If you think about having a negative x power here, if we look up here at like x, when x is like -5 or 6 or something, a negative power would flip this fraction over. So it was a 1/3, but it becomes 3/1 with a negative power. So 1/3 to the -6 is really 3 to the +6, which is why the negative powers cause this thing to get so much larger, and the positive powers cause it to get smaller and smaller. Some people start to think that this value in here has to be a fraction, but it's not that it's a fraction, it's that it's less than 1. If this was a fraction bigger than 1, like 4/3, if I was doing 4/3 to the 5th or something, like if x was 5, I'd be doing 4/3 times 4/3 times 4/3 times 4/3 times 4/3, which is going to be an ever-increasing number. It's not increasing by a lot, because 4/3 isn't much bigger than 1, but it's going to keep getting larger and larger until eventually it starts getting way larger, and that's exponential growth, because the value is bigger than 1. Not because it's a fraction, but because it's bigger than 1. This will be our last example. I'm going to graph this one. 2 times 3 to the x minus 1 minus 6. In my table, I want to think about smart points to plug in. Points that make this somewhat sensible and reasonable. So the 0, 1 point in this case is if I plug in a 1 for x. So if I plug a 1 in for x, 1 minus 1 is 0, and that's the first one I want to find. Whatever makes this thing equal 0, whatever makes this equal 0, that x minus 1. So 1 minus 1 is 0, 3 to the 0 is 1, anything to the 0 power is 1, so 3 to the 0 is 1, times 2 is 2, minus 6 is -4, so this is the point 1, -4. Now I'll plug in a 2, I plug in a 2, I get 2 minus 1 is 1, 3 to the first is 3, times 2 is 6, minus 6 is 0. I'll plug in a 3 to see if it fits, but these numbers get really big really fast. 3 minus 1 is 2. 3 to the second is 9. 3 squared is 9. Times 2 is 18. Minus 6 is 12. And I can barely fit that on. I've got the point 312. The next point I'll show you to see how quickly this gets large. If I plug in a 4, 4 minus 1 is 3. 3 cubed is 27. Times 2 is 54. Minus 8 is 48. So I have the point 448, which I definitely can't fit. I'll try and grab a couple points in the other direction. If I plug in a 0, 0 minus 1 is negative 1. 3 to the negative 1 is a third. Times 2 is 2 thirds. 2 thirds minus 6 is 5 1/3, or 5.33333. Plug in a negative 1. 3 to the negative 2 is 1 over 9, so 2 over 9 minus 6 is negative 5 8/9. I don't really know what negative 5 8/9 is, so I'm going to calculate that real quick. In fact, I'll just do all of that once. I'm going to do 2 times 3 to the, I'm plugging in a negative 1 for x, so it's negative 1 minus 6. It's negative 5.7777. I don't think this graph is going to let me throw things on. Oh, maybe it is. Let's see. If I take this, drag it over here. Hey, look, there's my points. What happened here? Should be the point 0, negative 5.333, excuse me. So this has an asymptote at negative 6, just like we would have guessed, because that's this negative 6 value right here. So the asymptote is the line y equals negative 6. And it's exponential growth because the base was bigger than 1, so it's going like that, real high. Okay, thank you.